Dr. Joseph Soriaga is a Senior Director of Technology who leads the system team at Qualcomm AI Research. The team is broadly responsible for driving hardware and software platform innovations, advancing applications in areas such as multimedia and wireless, and contributed to fundamental research in machine learning. Prior to this role, he led 5G core physical layer research team within Qualcomm wireless R&D, and also helped drive the standardization of 5G and a 3GPP Run 1 delegate. He received his BSc from Caltech, PhD ECE from UCSD with focus on coding theory, communication, and information theory. He was awarded IEEE Data Storage Best Paper in 2007 and the Eurozip Journal on Wireless Communication and Networking Best Paper in 2012. He has been granted over 280 US patents, which are amazing. Please, Joseph, welcome. Thanks to be here with us, and the floor is yours.
Yeah, thank you very much for the kind intro and being able to share with you today. I'm going to talk at length on a lot of work that's in our team at Qualcomm AI Research. There's a lot of great contributions. I want to give you kind of a broad aspect to this. Let me start with a little bit of background on Qualcomm and Qualcomm AI Research. So one very important priority for us is making AI ubiquitous at the edge. We can break this down into power efficiency from model design and quantization to the tools to enable the software and efficient hardware to use them on efficiently on hardware. And also the on-device learning, which is what we'll be talking about at length today. In addition to this, efficient learning is also important, and this is somewhere where the fundamental research comes into play, because for all the benefits we may have with better hardware and software, it's important that the algorithms and the use cases are not inefficient and kind of leaving us in a wash. We focus on things that can scale, so we may be at mobile, but we also look at adjacent areas like auto, IoT, and then we can scale to cloud and edge. Now, within Qualcomm, there's a Qualcomm AI Research, and this is where our team is broadly interested or holistically interested in working. And then you'll see how this is going to play out even in on-device learning as I go through the talk. But you can imagine it's easy to think about applications to start, like voice UI or multimedia, and applying machine learning and deep learning to these areas. But then there are fundamental areas like self-supervised learning or deep generative models. And understanding these techniques helps us to advance the applications that we look at. And you'll see self-supervised learning playing its role also in on-device learning. And together with this, we make sure that we keep an eye on what innovations at the platform are needed or how these might affect how the platform is evolving. So this can range from computing memory, which was a nice talk earlier from IBM, all the way to toolkits that we provide for model efficiency like AMIT or hardware and software co-design. And so things like on-device learning, you can see that there's an overlap in various areas, and our group is focused on making sure that we look at the system overall. And then one last important thing, just as a background to our group, is that we make sure to really build out proof of concept in addition to leading research. So this is really just a snapshot of, in one sense, how are we trying to contribute academically, but at the other side, how do we build it out? Because there's a lot that goes into proving it out on device with a lot of the things that need to happen. Like for instance, putting it on Android, we are contending with a lot of other things happening on the phone and making sure that we can deliver some of these advanced innovations and machine learning and deep learning are important from these proof of concepts. So that's the background on our team. For on-device learning, I think this is well covered by many of the speakers before. I think that the diagram is probably the important thing here, just level set, because you will see this as we continue to go through the talk. We will think of models being trained prior to deployment, and then we will think about adapting models once they are deployed and in various means. The benefits people have mentioned already. We can continuously learn, we can personalize, we have data privacy, and we also have a better scaling, which I can talk about in a few concrete cases. So the benefits are clear, that we can get better examples than we may have had in the training data set, or we can run with smaller models, interestingly, that can adapt to target data, and of course, privacy. These all come with challenges, of course. So local data can be limited. That's, I think, the most predominant one sometimes. The data itself too, if you do manage to get a lot of data, it can be noisy or unlabeled, or there's even an imbalance. We do want to make sure that if we are learning, we don't overfit or we forget important things that were trained offline. And then there's, of course, compute limitations, storage limitations. Interestingly, when we start enabling learning, it's important to make sure that that they can't be attacked, because there are some things that can be done to models knowing that they will be adapting to examples. And then finally, federated learning itself, there's further optimizations that can happen in communication overhead related to secure compute and just the model sharing and aggregation. So we're going to touch on a lot of these today. So you have a sense of the overall system design that needs to go in place, in addition to a lot of the implementation focus that happens in making these smaller and efficient at the edge. So here's a kind of an agenda of what we'll look at for today. So we have broken down local adaptation use cases into FewShot learning. So when you have a few examples and they're well labeled, or continuous learning, where you may have a lot more examples, but they are unlabeled or weakly labeled, and we have to somehow leverage them with unsupervised learning. These two will be more in a local sense. When you see what's involved and what's enabled, it's very natural to start aggregating and then federating them. So we talk about how we do federated learning at a larger scale. I think many are familiar with this already. So we'll be more about examples and particular design considerations. And then we'll end with looking at low complexity aspects with, say, model design, or how we implement backpropagation and so forth. All right, so let's start with FewShot learning. This was given example earlier too with this transfer learning from Coral. So suppose you have a few examples and they're well labeled. How can we benefit from that? So we think about what are the use cases that actually would fundamentally improve the KPI that's needed. And so this was a nice example that we came across, and it's nice to share to get everyone a sense of the system design that goes behind it. So in keyword spotting, you can imagine that this is a place where we really do want a very small model, because it's going to be listening all the time for a user to say a keyword like, hey, Snapdragon. And the challenge here is that there's a lot of diversity in how people say a certain keyword, and there's a lot of diversity in keywords as well. And pre-training to cover this diversity has some challenges. So one is you may not even have the diversity in the data set that you have. But interestingly, also, if you do have the diversity in the data set that you have, you still want a small model. So a small model may not be able to really capture all of that diversity in your data set. So an alternative way to deal with this is to allow the model to adapt with a few key examples on the device. It allows it to stay small. And in this particular application, the keyword really needs to only respond to the target user. So it may be a bit of an overkill to have a large model that has a lot of diversity if there's really only one user at the end that's using it. So in this example, outlier users can sometimes have 30% worse detection rate relative to like inlier users. So generally, what we did was we captured a few examples of the speakers. They're prompted to say the keyword. And then we can essentially fine-tune the model to that set of that particular user. And then if we look at doing this across a test set of users, we can see that the outliers were able to improve considerably. Meanwhile, we have that the inliers, they had some small gain. Of course, they were represented well in the initial data set, so that they were already fine. But nothing was made worse, so everyone generally got better. And so this is an example of this personalization really fixing kind of the broken parts of the system and fundamentally kind of making our system better overall. And I don't have this in a slide, but interestingly, we did a study too to see, what if you were to send data, up to the cloud and then train and send it back to the cloud. And you can imagine that is quite, that can be also a way to scale personalization, but it can be quite expensive if you didn't have a privacy constraint, for instance. And so this is really helping to enable, a benefit beyond that. So the next thing you can think about is, suppose you don't have labeled examples, but you can get a lot of them. So this is more continuous learning. And the challenges here are that we may not have a clean environment. We may not have a good sampling of the data. It might actually be skewed in the distribution. And we wouldn't want to forget what we're doing, what we've learned in the pre-training. So one interesting use case that we looked at more closely is in semantic segmentation. So in this particular case, you like to label pixels with certain classes. And then when we look at video, smaller models at the edge tend to flicker frame by frame. And so this can really affect the tracking in, say, XR applications or mobile applications. And is there a way to fix this? So interestingly, there's an on-device learning way to fix this, where you can adapt the model as you see the video happening. The other way to fix this, of course, is to make the model bigger. And then the model will get more accurate. It'll be more power consuming, but then the flickering can also go away that way. So with the larger model, of course, the computation can be prohibitive. And then with previous solutions with on-device learning, they were somewhat expensive because they're modifying them, a larger model, and also they may drift, and we do want to be able to control that accuracy. So the solution that we looked at in leveraging on-device learning was, what if we had a main network that essentially establishes the high accuracy of segmentation? And we have a smaller network that we can adapt to the video as it's coming. And the outputs of these two networks, we combine them so that we can make decisions that are now adapting to the videos themselves. And the smaller network can help in updating so that it maintains a lower certainty, or it focuses on lowering the uncertainty and making predictions. And so this is the technique that was published, that's to be published. And now the challenge with this now is implementing this technique. So this is essentially requiring that we're updating according to the video that we're seeing in real time as we're seeing the video. Amazingly, the state of progress with technology is that we can do this where we have a fairly accurate segmentation model running through, on this diagram on the right, running through our DSP and a Snapdragon AI engine. And then as it's going through the DSP, it's making decisions on the segmentation, but then we can also do that small network adaptation. And we can do this on another processor. In this particular case, we did it on the GPU, and then those outputs are being combined and making the overall decision. Meanwhile, the GPU is also being used to update the model, the AuxNet model, every 10 frames, essentially. And so this is able to improve the MIOU, improve what's known as the temporal consistency, some measure of the flickering. And then in some video demos, which you can see offline if you kind of search for this at CVPR, there are examples where the segmentation can be really, the flickering can be really off. And it's even though the number may seem small here, perceptually it's very obvious, the mistakes that are being made before we add this AuxNet. And then to be able to do this with a larger model is considerably more compute, even if you take into account the amount of backpropagation that's being used. It's something like tenfold or so in our paper. So this is an example of how we can use continuous learning, making sure we don't drift too much, but we're actually enhancing the bottom line KPI of segmentation performance. Now, going a step further, now that we can look to train on device, we can think about aggregating these with federated learning. And in some cases, data is not as diverse within one user, or there are not as many examples. So it is nice to be able to aggregate so that we can have a better global model. One particular example that is a nice kind of exercise to go through is looking at user verification. So in user verification, you want to have some kind of biometric, many can be thought of as images, like face and fingerprint are naturally images, but even voice spectrogram is essentially an image, and some other medical measures can be images too. And ideally, in user verification, you do have to know what the difference is between users. But if you're going to federate it, you can't let any single entity see more than one example. They have to keep all the data local to each user's device. So it's interesting to understand, can we actually train a model to know the difference between people if the model is never being trained in any instance to separate the differences between users? You can normally picture this on the right too. So the idea is like data is coming in, and then we're going to get a scoring, and that scoring, we want them to be close to different users, but then we want the regions with respect to each user to be separate and well distance away from other users, so that we can improve that user verification. And so nominally, one of the interesting things that was observed from the research in this is that we can actually develop a method to train user verification without sharing embeddings between the users. So in nominal solutions, even though the data is not shared in federated learning, sometimes people still do send all the embeddings to the users themselves, so that the users, when they train, they have a loss function that can ensure the separation between other users, or maybe a set of imposters. But here, only positive loss is done. So each device is training just to be predicting their local user, And then embeddings are shared in an interesting way using error correction codes to ensure that they're not shared, but they're picked according to using error correcting codes so that we ensure that they're far away from each other. And by doing this, the team was able to show that we can use federated learning to actually train something to differentiate users without ever giving an instance of different users to any training entity. And then there was some quantification of this relative to state of the art where you are sharing embeddings. So this light blue softmax is essentially if you were to share these embeddings, and then this user verification is if you didn't share the embeddings and you use this approach from the paper. And then there's some other approaches that were published, and they're also a little bit worse than where we were at. The last part of federated learning is really putting this on device and putting this into a system, because frameworks at scale are not really provided for the research community, we feel, or general application developers. So we've been working on putting this into our own mobile devices and Android, and putting this into a system also where there's a coordinator, there's a way to insert these libraries into PyTorch and TensorFlow, and allow this to really work over a connection protocol with TCP/IP. So we could do this on cellular or Wi-Fi or so forth. This is something that we were able to demonstrate last year at the end of the year. We had something at NeurUps at our kind of our virtual booth, and it involved using commercial devices. So the state of the device capability was such that we could already implement this on last year's Galaxy. And we did something very similar to what I talked about in a few slides ago, is we can train user verification with 1,000 different clients, essentially. This is showing you a bit of like the system design behind it, and also trying to develop this for experimentation. Now I'll switch into talking about this complexity aspects. Backpropagation is many of the other speakers have said earlier, can be expensive, and it's natural to see how can we make these simpler. There's the forward pass, which also stores activations in many cases that get leveraged in the backward pass computation. And so there's various things that have been talked about, like can we selectively pick the last layer or different layers and just update those, from more of an algorithmic or a system aspect. And then there are also things about what can we do implementation-wise to address these requirements on backpropagation. So again, we're thinking like we have large memory, we have training runtime, we have a need for higher precision. And then at the edge, we always want to be able to still come back to quantized inference, because that is the most power efficient way to be able to, and that's the most, that's the workload that's taking up the most power, is the inference. So I'll touch on a few of these. We can reduce the complexity of backprop with quantized training, much like quantization helps inference. We can do that for the training side. We can make the models more efficient for backpropagation. So I'll be more specific about that. Not just making them smaller, but being able to trade off storage and memory with compute. And then I'll mention it here, but we don't have it in a slide. It's more of in our research papers. You can also adapt the model using inference. So you can maybe prune on the fly or select some things based on examples that you're seeing in the test data. So the first one, the first example is looking at quantized training. So as we know, quantization can be implemented very efficiently in both area and in power. And also it can reduce the bandwidth exchange that's needed. So it's a very natural thing to think about in applying to training. The range, though, that needs to be used is quite larger on the training side. So being able to dynamically change ranges is important on the backpropagation computations. And so the question is, how do you select these ranges? So one way that has been thought about is, as you get batch statistics, you can calculate those statistics on the fly and then apply the quantization to the metrics that you're calculating as you're going through the MAC operations for backprop. And so the drawback, though, is that you kind of now required a lot of memory to store, to figure out the range and to get the statistics. But it turns out that you can do this as part of some of the calculations you're already doing, and then just have a delay. And so, for instance, as you're accumulating, you can just develop these statistics on the fly, and then apply them in the future to the next iteration of backpropagation. And so we term this in hindsight range estimation, and this allows us to significantly reduce the memory transfer that would have been needed if you did it each in time as you were doing your backpropagation. And then another important angle is how do you reduce the memory through just allowing more compute? So, in a neural network, we have this backpropagation you can break down into these differentials, these derivatives that you have to take. And so the activation is what needs to be stored as we propagate backward. It so happens that there are a lot of examples in models without changing them where you can calculate backward and you don't have to store anything, but the model itself is not fully invertible. So the question is, can we make a model that really can be fully invertible or really dramatically reduce the amount of memory that you need to store? And so that's what our team did here, is they looked at MobileNet, and to be competitive with MobileNet, it was important that we keep the same number of parameters, we keep the same number of MACs on the inference side, and we keep the same accuracy. And looking at all three of these KPIs, many of the approaches to making models invertible didn't really maintain them. So either the MACs have gone up, so the inference was a little bit more expensive, or the parameters went up, so the inference was a little bit more expensive, or the accuracy went down. But what the team showed was that you could actually introduce these invertible layers that I show in this diagram, or variations on them, and also handle pooling in a certain way, such that we could come up with an invertible network, largely invertible, where you store 11x less activations in the memory when you do a backpropagation calculation. And so this allows us to, if you don't even have that much memory on the chip, or that's the expensive thing, is moving memory on and off the chip, we can really save power or reduce the latency in doing these things. And of course, you don't have to use this. So the nice thing is, if you do have a model that does this, software can be the one to decide how much of it do you do compute, how much of it do you do storage. But at least the model itself can be architected in a way that's beneficial. And so that kind of gives you a sampling. We do have many other things that our group looks at. I think that it's a very rich area still for research. At the same time, there's good progress and stability towards being able to start deploying some use cases that are getting more and more sophisticated. Some things that we are, have published that we haven't talked about here, improving the communication in federated learning, or looking at different topologies in federated learning. And also, how do we deal with statistical heterogeneity in data, or dealing with noisy labels. There are other ways that we deal with noisy labels and make more robust systems that learn at test time. So with that, I'll conclude. Thank you for listening. Generally, we do feel like everyone here that bringing learning to the edge is crucial, and there's a lot of great research opportunities as well as development opportunities in this. And I'd be happy to kind of take any question if you have.
Thanks, Joseph, for your great talk, and really you touched a lot of important point when addressing ODL. I don't see questions in the Q&A chat. I have a couple of for you, kindly.
Sure.
One is quite general. Mm-hmm. In which application domain or in which context do you believe on-device learning can express its full potential and therefore is mandatory to be addressed?
Yeah, that's a great question. I think a couple of them are kind of what we touched upon, where if there's say more sensitive data that we would like to learn upon, there's a opportunity where on-device learning has a very strong advantage, I would say. It's important to know that there's a lot of attacks on a particular problem. So sometimes people will also want to say reduce the amount of data such that it's essentially anonymous and then still centralize it, which is another solution to certain things that do limit privacy. But if you do have the compute, it can be a more complete solution to just be able to do it completely at the edge and learn when needed. So data privacy is one where potentially it's as close to mandatory as you say. Other ones are the connectivity. I think that in some of the IoT examples earlier, sending data may not be so easy to do at test time to a central cloud, just because the connectivity may not be as reliable or the bandwidth may not be as high. So that's where those kind of use cases will be more of more compelling to have on-device learning kind of enabled at the edge.
Thank you to elaborate. And the second final question. In your opinion, in your experience, from one side, accuracy advantages, and from the other side, the constraints regarding the implementability on a certain execution target. Are these, sometimes these are conflicting each other, no? And in your opinion, in the on-device learning, should we pay attention to both, prioritize one versus the other, compromise one versus the other? What is your general opinion on that?
Yeah, it's a great question. We should always think of both. I think it's understandable, depending on the research effort or the development, the developer effort. You may not be able to cover both as much as you'd like, and you can imagine just going into implementation itself can be quite involved. But at some level, having that notion that we do, in the end, the application developer, there's going to be some application that really needs to benefit from doing this. So we're going to be competing with, at a performance level, at accuracy level, with other, approaches to trying to solve the same problem. And so it's important to make sure that we can be competitive on the accuracy. And that's why I kind of picked some of these examples, because some of the examples, we are, like, for instance, this keyword spotting, we are trying to compete with, some people would like to have a solution where they do centralize the data and they find some way of being able to send the data essentially. And then in the end, it's still going to be, we can maintain the same accuracy, but it will be less compelling because you end up with a bigger model in that particular case, or you end up spending a lot of bandwidth to send a bunch of small models to a bunch of different users. So there are going to be these very unique, I would say, like winning points for on-device learning. We just when we think really about the target application, but we can't get there unless we really make sure that we're able to deliver, the best accuracy that we can, as well as the best implementation that we can.
Appreciated, Joseph. Thanks again for your time, for all your words and explanations, and to share your research interest on on-device learning, also on behalf of Qualcomm. Much appreciated. Thanks. That forum was possible thanks to the tinyML Foundation support and all the support from the strategic customer, which are helping a lot in providing resources to make sure that this forum and other events and other interesting events will happen in the future. So just to thanks also and list the executive strategic partners: ARM, Edge Impulse, Qualcomm Research, Sentient, and the Platinum Strategic Partners: DeepLight, Clickattack, Reality AI, Renesas, Sony Semiconductor, the Gold Strategic Partners: Analog Devices, PhotoHub, Microsoft, NXP, Seed Studio, Sensimil, ST Microelectronics, Synaptics, ScienceSense, and all the silver strategic partners. Thanks again to stay with us yesterday and today, and I hope it was a valuable experience. Thanks and see you soon. Bye.